Hello everyone, welcome back. Today's lesson 321, and again we're going to focus on rewriting, but this time we're going to focus on exponent rules. All right, so this is kind of a review from Algebra 1, where we're going to talk about what the definition of an exponent is and how we can use some of the rules that we learned back in Algebra 1 to rewrite certain algebraic expressions that involve exponents. Okay. So let's kind of get into the basic definition of what an exponent tells us. So in this first example here, we have a variable a being raised to the fifth power. So what that is telling us, this little number up here, that is our exponent. And what that number is telling us is that we're taking a and multiplying it by itself 5 times. Right? So I could rewrite a to the fifth power as a times a times a times a times a. If I had a to the second power, then I would have a times a, right? So I'd have 2 multiplications of a. If it were an exponent of 3, then I would have 3 multiplications of a. All right, so this exponent tells you how many times you're multiplying that base by itself. All right. So let's talk about this one. This one's an example of a product, right? So we're multiplying two things that have the same base. So when I talk about the base, I'm referring to the number in the bottom here. So you notice how they both have a 2. And we can see the exponents of 2 and 3 here. All right, so let's rewrite this in its expanded form, just like this, right? So rather than writing 2 squared, I'm going to write 2 times 2. And then instead of writing 2 to the third, I'm going to write 2 times 2 times 2. Right, so I've got 1, 2, 3, 4, 5. Right, so I could rewrite this a little bit easier. Rather than saying 2 squared times 2 to the third, I could just say 2 to the fifth power. Right, because I had 2 times 2 times 2 times 2 times 2. And if you noticed what happened there, right? If you notice the pattern between the 2 and the 3, it seems like all we did there was added the 2 and the 3 to get our new exponent of 5. Right? So if we run into a problem like this, rather than writing 2 times 2 times 2 times 2 25 times and then another 45 times, I could just use that little rule and add my exponents. Right? So this is going to be 2, and then 25 plus 45 would be 70. So this will be 2 to the 70th power. So when we multiply something with the same base, all we have to do is add the exponents. So this will be a to the m plus n. And that is what we call the product rule or the addition rule with exponents. Okay? So when you're multiplying something with the same bases, add the exponents. Right? So this one takes care of a quotient. Quotient is a fancy math word for fraction, right? So this is a fraction here in our example, and it says with the same base. So you'll notice in my exponential expressions here that the base is a. So it's the same between both of them. All right, so if I were to write this out in its expanded form, right, instead of writing a to the fifth, I could do a times a times a times a times a, right, 5 times. And then in the bottom of my fraction, I could write a times a times a. Right? And then I could cancel things out, right? So any common factors that are in the top and in the bottom, we can cancel those out. So these a's will cancel and become 1. These a's will cancel and become 1. These a's will cancel and become 1. And you'll notice that all we're left with in the top there is a times a, which is a squared. Bottom of our fraction will simply have a 1, right? Because 1 times 1 times 1 is 1. So notice that we had a to the fifth divided by a to the third. We got a to the second. Okay? And if you're hopefully noticing that pattern, what we did was we subtracted the exponents, right? I took 5 minus 3, got a 2. Okay? So rather than doing something like this where I would write out a 300 times and then a 50 times and cancel them all out, I could just write this as a and then subtract 300 minus 50, so this will be a to the 250th power. and it's a lot quicker than writing it out like this. So if I can remember this rule where I know I'm going to subtract the exponents, I can save myself a lot of time. Right? So if I have a situation like this where I have the same base, I can figure out what my new expression is going to be by subtracting the exponents. So we would do m minus n. All right. This next rule is called power to a power. All right, so you'll notice here in my example that I have x squared raised to the third power, right? So it's x to the second power to the third power, which is why they call it a power to a power, or an exponent to an exponent. All right, so when we raise something to the third power, whatever it is that we're raising to the third power, we need 3 of those things, right? So everything in the parentheses is getting raised to the third power, so we're going to say x squared times x squared times x squared, right? There's my 3x squareds. That's what's inside the parentheses. Now, x squared is the same thing as saying x times x, and then I have another x squared, so I'll do x times x, and then I have another x squared, so we got x times x, and then I count them up. 1, 2, 3, 4, 5, 6. So I could rewrite this as x to the 6th power. And I would compare this exponent to the numbers that we see up here. So we had a 2 and a 3. We ended up with a 6. So it seems like we multiplied these exponents, right? Because if I do 2 times 3, we get a 6. All right, so again, that's handy because if I have larger exponents, like if I have 10th power and a 5th power, well, I mean, I would have to write out x to the 10th 5 times, and then I'd have to break all those down and do x to the 10th and x times x times x times x times x, who knows how many times. But I could just use my shortcut here, write this as x, multiply these two, right? 10 times 5 is just 50, and I could avoid all of this, right? So when we see a situation where we have a power to a power, I just rewrite it with the same base and multiply the exponents. All right. The next property we're going to talk about is what's called the zero power. All right. And guys, I can't stress this enough. This is the easiest one of them all. If you take anything at all, and you raise it to the 0 power, it's always going to be 1. It doesn't matter what it is. It could be 32 to the 0 power is 1. 48 to the 0 power is 1. Okay? It doesn't matter what number it is. It doesn't even matter if it's a variable. So if you do x to the 0, it's 1. If you do z to the 0, it's 1. All right? Anything raised to the 0 power is 1. All right. This next one can get a little bit tricky. It's our negative exponents rule. So sometimes we can raise something to a negative power. I know that seems weird, but if we do get something that is raised to the negative power, what you do is you take the reciprocal, right? So I take this x to the third and I flip it, right? Because this is x to the negative third over 1, so I'm going to flip it and say 1 over x to the negative third, and then you take away the negative exponent. Okay, so you just take away the negative and say x to the third. So you flip it and get rid of the negative on the exponent. All right, so that's what they mean here by reciprocate the base. That means that's the flipping, and change the exponent to be positive. That's where we got rid of the negative sign. Okay, so if I had something like this, like a to the negative b, I would rewrite that as 1 over a to the b. Right, so I flip it, right, pretend like this is over 1, I flip it, and then change that b to a positive exponent. All right. All right, last property here that we're going to talk about is what's called fractional exponents / radical expressions. And this is going to seem weird, but we have seen square roots and cube roots and things like that before in previous lessons. What you guys didn't realize about those was that they are actually exponents, right? So for instance, a to the 1/2 is the same thing as the square root of a. So this square root symbol is actually telling you that a is being raised to the 1/2 power. Most students don't realize that until later on in college, but that's what a radical is. All right. Now you can get more complicated fractional exponents such as this one, right, where we have 3 raised to the 4/5 power. Okay, let me show you how to handle that one. So we have 3, and since it's a fractional exponent, we're going to have a radical like this. Now, this is not going to be a square root. The number in the bottom tells you what kind of root you're going to take. So this is going to be a fifth root because the number in the bottom of the fraction is a 5. The number in the top of the fraction tells you what power to raise this number to. So this will be 3 to the 4th power inside of a fifth root. I know that seems weird, but let's take another look at this one, right? So if I did the same thing on this one, right? There's my radical, there's my variable. This would be a second root, which we always call a square root, and the a would be raised to the first power, right? So if you think about it, a to the first is just a, and a second root is just a simple square root. Okay. So we could go the other direction, where we start with a radical and rewrite it as a fractional exponent, right? So this is going to be x raised to the something over something, right? I'm going to put a fraction up here in the exponent. Now, since there's a little 6 here on the radical sign, okay, that 6 tells me I'm going to have a 6 in the bottom of my fractional exponent. X is just written by itself without an exponent, so it's being raised to the first power. So I'm going to put a 1 in the top of my fraction. So the 6th root of x is equal to x raised to the 1/6 power. So our general rule here is if I have a fractional exponent, I can rewrite it as such, right? I have the nth root of a to the m power. Okay, so why did we take all that time to talk about rules of exponents? Because we are going to be talking about how to simplify rational expressions such as these, okay? And knowing those rules of exponents can be really, really helpful. All right, so for instance, with this expression, if I wanted to simplify it a little bit, I could rewrite it as 3 times x over x, and we can see that we get a set of x's to cancel out to be 1. So this would simplify to be 3x over 1. Okay. Now it's important to keep in mind that when we do cancel things out in fractions like this, only factors cancel. Okay, so you see an x minus 3 in the top, that would only cancel with another x minus 3 in the bottom. Okay, so I can cancel out an x minus 3 here and an x minus 3 here. Those cancel out to become 1. In the top, all we have left is x plus 2, and in the bottom, a 1. Okay, so this expression simplifies to this, which is easier to work with, but we have to remember how things cancel out in a fraction. So here in part C, we have another rational expression, and we might be looking to cancel things out. A common mistake that a lot of students will make is they will just try and cancel out the x's like this. But you can't do that here, okay? Remember, only factors can cancel, right? Factors are things that are being multiplied. All right, so when we look at this expression in the top, we have to treat this 2x minus 4 as an entire number. A 2x minus 4 will only cancel with another 2x minus 4 in the bottom. And since we don't see another 2x minus 4 in the bottom, we might assume that nothing is going to cancel. However, we can rewrite this top expression. Okay? I could rewrite that top expression as 2 parentheses x minus 2. So in other words, like factoring out a 2. Okay, so these two expressions are equivalent. And I can prove it because I can take 2 times x and I get my 2x, and if I do 2 times negative 2, I get my negative 4. So it's like all I did was the opposite of distribution. I just pulled a 2 out from each term. Now, in the bottom, we still have an x minus 2. Right, so the x minus 2's will cancel because I have one in the top and one in the bottom, and those are factors. So this is going to cancel to be 2 over 1. All right, so there's our expression. And we're going to talk more about these. I know that might be a little confusing at first, like, wow, you're canceling out x minus 2's, but we couldn't cancel out x's over here. Getting used to what cancels and what doesn't cancel is going to take a little bit of practice. It's going to take, just going through some problems and getting used to it. So don't be intimidated right now. All right, these are just real simple examples that we're doing. It's just the beginning of this particular topic, so we're going to get a lot more practice with it. All right, so let's take a look at another example. what we're going to do here. And I kind of gave you a little step-by-step here. So we're going to simplify rational expressions. All right, it's the same thing as reducing a fraction. First thing we're going to do is we're going to factor the numerator and the denominator as much as possible. In other words, we want to find factors that will cancel. Okay, and once we find common factors in the top and the bottom, we can cancel those out. Now, right now, we cannot cancel anything out with the way that this is written. So a lot of students might try and do this, right? They might try and cancel out the x's, like, hey, there's an x up here and there's an x down here. But the problem is this addition stuff. Okay, we have things that are being added. We don't have things that are being multiplied. Factors are things that are being multiplied. All right. The way that I like to go about this is if I see an expression like this, like an x plus 3, I put that in a pair of parentheses and I remind myself, x plus 3 needs another x plus 3 up here to cancel with. Right now, with the way this is written, I don't see an x plus 3. But I can rewrite the top by factoring. Okay, that's what they're talking about up here, number 1. It says factor the numerator and the denominator as much as possible. So I'm going to factor this thing using a box and diamond. There's my box. Here's my diamond. Okay, so I'm going to take the x squared, goes in the upper left-hand corner. I'm going to take the 6, put it in the bottom right-hand corner, and the 5x goes in the bottom of my diamond. And then I multiply the diagonal. Oops, and that should just be a 6, not a 6x, my bad. All right, so we get a 6x in the top, so I'm looking for two numbers that multiply to give me a 6 and add to give me a 5. Okay, so those two numbers are going to be 2x and 3x. All right, 2 times 3 gives me 6. 2 plus 3 gives me 5. Okay, so I'm going to put a 2x here, 3x here, and then I'll work on my outside dimensions. X times x gives me x squared. X times 2 gives me 2x. X times 3 gives me 3x. So if I'm rewriting the top, right, that word rewriting comes up so much. Right, here across the top I have an x plus 2. And then over here on the side I have x plus 3. All right, so there's my new way of writing this. I rewrote this in its factored form, and in the bottom I have an x plus 3. Now I have a common factor that I can cancel out. This x plus 3 will cancel out with this x plus 3, and we get x plus 2. Okay, so that is my reduced or simplified form of this expression. All right, like I said, we're going to talk more about that later, so don't stress it too much. Just come back and watch this example if you need to a couple times as you work through the practice problems, and make sure you ask me questions in the Zoom chat. All right, guys, good luck. Have a great day.